Hello, and welcome to the last chapter. Congratulations, you made it to chapter 15! Yay! Claps for all. Alright, so this chapter considers test of hypothesis for nominal, basically, level data. Non-parametric hypothesis tests do not require the assumption that the population be normal. First, we're going to consider two manual exclusive groups, then several mutual exclusive groups. We're going to use the chi-square distribution as a test statistic in this chapter 2, because we're going to just throw you a last more item to calculate in the chi-square. Why not use another chart? So again, drill is, we're going to test a hypothesis about a population proportion. We're going to test a hypothesis about two population proportions. Test a hypothesis comparing an observation set that we see. So we're going to compare a frequency to an expected frequency distribution. Explain the limitation of using the chi-square statistic in goodness of fit test, and then performing a chi-square test for independence on a contingency table. Yes, the contingency table is back. We've seen those before a long time ago in a galaxy far, far away. So, test the hypothesis of a population proportion. Okay, we're going to recall that proportion is the ratio of the numbers of successes to the number of observations. Again, we're going to basically assume the binomial assumptions that we've discussed in prior chapters. So, examples that we can use. Historically, GM reports that 70% of leased vehicles are returned with less than 36,000 miles on them. A recent sample of 200 found that 158 had less than this amount. Has the proportion increased? We're going to check. Again, these are just examples, just questions that they give out. Like Able Moving and Storage advertises or advises its clients that their household goods will be delivered in 3 to 5 days for a long-distance move. Record shows this is true 90% of all the time. A recent sample of 200 moves found that they were successful 190 times. Has this success rate increased? Again, we can observe from the sample size. All we're doing is finding the ratio of successes to the number of observations. So now we get to test this. So, the test of hypothesis about population proportion, the binomial conditions must be met. The sample data collected are the results of counts. The outcome of the experiment must be classified in one or two mutually exclusive classes. The probability of a success is the same for each trial. The trials are independent. Both n pi and n times 1 minus pi must be at least 5. And this is our test statistic. Notice it brings back z. Z equals our proportion minus pi divided by pi times 1 minus pi divided by n. Okay. So how does this work? Well, let's look at it, because of course we can have an example. So a Republican governor of a western state is thinking about running for re-election. Historically, to be re-elected, a Republican needs at least 80% of the vote in the northern part of the state. The governor hires a polling organization to survey the voters there. Polling organization will poll 2,000 voters, using a statistical hypothesis testing procedure to assess the governor's chances of winning re-election. So state the null and alternative hypothesis. Well, we know we need at least 80%. So pi is going to be greater than or equal to 0.80, 80%. So the alternative is that if the governor's going not win, it has to be less than 0.8. Okay. The level of significance we're going to be using is 0.05. Again, most common one. And since we're dealing with greater than and less than, we have a one tail, as shown in our little chart there. We're going to select the test statistic. We're going to use Z. And since, again, going back to Z, we'll find that using our chart, that the critical value is 1.645. Or, since we're doing a less than, negative 1.645. Okay? That's basically the alternative. When it's less than, it's a negative. So the decision rule is we're going to reject null if Z is less than negative 1.645. So take your sample, make a decision. Okay, using our formula or proportion. 1,550 divided by 2,000. Apparently, the poll, the survey actually revealed that 1,550 planned to vote for the governor. Yeah, they didn't put that in the sample, in the question, but really they did. They polled, apparently 1,550 said that they will vote for the governor. Divide that by 2,000 and minus 0.8. Well, 1,550 divided by 2,000 equals to 0.775 minus 0.80. So we're going to show a little bit of a negative there. And we insert our pi, 0.80, times 1 minus 0.80 divided by 2,000, the number of people we surveyed. We find out that it's negative 2.80, which means we're going to reject the null because it is less than our Z value of negative 1.645. So interpret the results. The governor can conclude that he does not have the necessary support in the northern section of the state to win re-election. So he needs to probably run more advertising, see what's going on up in the northern part of the state that he needs to win. Two sample tests about proportions. We can also test whether two samples came from populations with an equal proportion of success. Examples. The Vice President of Human Resources wishes to know whether there's a difference in the proportion of hourly employees who miss more than 5 days of work per year at the Atlanta and Houston plants. Woo! H-Town is in the book. A consultant to the airline industry is investigating the fear of flying among adults. The company wishes to know, is there a difference between the proportion of men versus women who are fearful of flying? Again, in both of these cases, each sample item and individual can be classified as a success or failure. In the next example, we will assume that each sample is large enough for a normal distribution. So let's use our testing statistics with a pooled proportion. So to test whether two samples come from populations with an equal proportion of success, first pool the two sample proportions using the following formula. So we have our pooled proportion. We're going to take our x1 plus x2. Okay. So again, these are the number of successes. And each one we're going to add them, and then add n1 plus n2, which gives the number of observations. Then we compute the value of test statistic from the following formula. Taking our proportion of 1 minus proportion of 2 divided by the square root of the pooled proportion times 1 minus the pooled proportion divided by n1, and do the same for n2. All square root. Yay! So you know where this is probably leading to. Probably a t-test, or, not a t-test, a z-test, but probably a to-tell, especially if we're looking at equals. So, a business researcher is studying online shopping and would like to know if there is a difference in the population of men and women who made an online purchase last year. The research sampled 100 women and 200 men at a 0.5 significant level. Is there a difference in the proportion of men and women who made an online purchase? Okay, we already see the statistics right there. About 81 women out of 100 did make a purchase. 138 men out of 200 made a purchase. So, our null and alternative. What we're doing is that we're saying that both proportions are equal. Pi 1 equals to pi 2. Well, alternative, of course, they do not equal. And again, we have this to-tell. Select 0.205. Remember, this is the total shaded area. So total of two tails. So we have to divide by 2. So our shaded area, where we're going to reject the null, is now 0.025. Again, if we look at our z table, now it's been a while, we're going to reject if z is going to be less than negative 1.96 or z is greater than 1.96. Next, we do all the math. You're like, oh no. Like I said, biggest thing when we have something like this, try to insert it into Excel. This way that all we have to do is put in the numbers and boom, everything calculates. Which we'll probably do with the practice problems. Since it's a little bit different than chapter 14, which they really just gave us the numbers already in the practice problems, and we didn't really go through Excel too much. Except when you do, you use regression analysis, the data analysis, yes. Alright, anyway, I'm off topic. So, making our business decision, first we do have to come up with the proportions. So 0.81 and 0.69, because they're going to be used for our z right here. We have to come up with the pool. So we take 81 plus 138, divide by 100 plus 200. So 219 divided by 300 equals to 0.73. So we subtract our two pools individually and use our pooled one. So proportions individually are pooled. A pooled proportion is down here on bottom. It comes out to 2.207, which is greater than 1.96. So we interpret by working women and stay-at-home women will purchase heavily at different rates or proportions. I don't know how they get. So yeah. Yeah, we should actually reveal. Yeah, this should be the working. Now, interpret that men and women will purchase heavily at different rates or proportions. I think the book had an older example that used the same numbers, and they decided to forget to change some of the things. Yay. Alright, goodness of fit test. We can compare an observed frequency distribution to an expected frequency distribution. Again, this is going to be using pretty much probably our new one, Chai, soon. Yes, Chai. Alright, so example. An insurance company wishes to compare the historical distributions of policy types with a sample of 2,000 current policies. Does the current distribution of policies fit this historical distribution, or has it changed? Okay, so here's our information. Of our whole life is 40%, level term is 25, decreased term is 15, other is 20. That was just an example. So now they actually have the real example. Always love how they do those kind of examples. Alright. So, our actual example in the PowerPoint. Goodness of fit test example. We got Bubba's Fish and Pasta. It is a chain of restaurants along the Gulf Coast of Florida. Bubba is considering adding steak to the menu. Before doing so, he hires a research firm to conduct a survey to find out what the patron's favorite meal is when eating out. Here are the results of 120 adults. Okay, so frequency, we have 32 for chicken, 24 for fish, 35 for meat, and 29 for pasta, to give us a total of 120. Okay. Is it reasonable to conclude there is no preferences among the 4 entries? So, if there's a difference in the number of times each entry is selected due to the chance, or should we conclude that the entries are not equally preferred? So, if we're concluding that there is no preference among the 4, this is where we get the expected frequency. That's why we have 30 for each one. As we can see, observed and expected are a little bit different. So, of course, we're going to have to test this. So let's test. So step 1, our hypothesis. So our null is there is no difference when adults are selecting their entrees. The alternative is that there is a difference. We're going to take, select the level of significance. We're going to do 0.05, and then select the test statistic. We're going to use chi-squared, which looks like a giant X squared. Alright, so we're going to formulate the decision rule. 1, we know it's 0.05, but how did we get degrees of freedom? Well, for us, degrees of freedom is k minus 1, which again, k is the number of items we're testing. So since we have 4 minus 1 will give us 3. So in our chart, on the 0.05, this means chi-squared is 7.815. So it's going to be this tiny little part right here on the scale. Kind of looks more like the F distribution, but this is the chi one this time. Okay. So, chi-square, what is it? Well, it's the characteristics of the chi-square distribution are as follows. The value of chi-square is never negative, just like the F distribution. There's a family of chi-square distributions. The chi-square distribution is positive skewed, kind of like the F. As the degrees of freedom increase, the distribution approaches a normal distribution. So instead of like F, which is stayed mostly to the positive skewed, we can see as we increase, the bell curve starts to actually change a little bit. Starts to become more normal. Step 5, we're going to make a decision. This is how we calculate chi-squared. Okay, so it's a sum of our frequency minus our expected frequency squared divided by our frequency expectations. So, another one that we would probably use Excel to help calculate by going step by step. Alright, after they calculated, 2.2 is our chi-square value. It is not greater than 7.815. So, interpreting the results, we conclude that the difference between the observed and the expected frequency could be due to chance. The data does not suggest the preferences among the 4 entries are different. Okay, since we didn't reject it, we can actually leave it up to chance. Again, chi-squares usually are using for proportions. Alright, hypothesis test of unequal expected frequency example. Okay, so this one is a little bit different. Okay, instead of thinking that, oh yeah, there's no difference, they're all the same when we expect it, we are actually going to show a difference. So the Animal Hospital Administration Association reports the number of times senior citizens are admitted to the hospital during a 1 year period. 40% are not admitted, 30% are admitted once, 20 are twice, and 10% are admitted 3 or more times. Then a survey of 150 residents of Bartow Estates, a community devoted to active seniors located in Central Florida, revealed 55 residents were not admitted, 50 were once, 32 were twice, and the rest of the survey was admitted 3 or more times. Can we conclude the survey at Barstow Estates is consistent with the information reported by AHAA? Now, biggest thing that we have to do is we're going to take the survey size and times it by the percentage that was emitted by the correct results, and it comes out to these numbers right here. This is our expected. Notice that it's not all equal. We already can see that there's a very close correlation between the two, though. So again, we're going to state the null hypothesis. There is no difference between the local and national experience. And again, the alternative is that there is a difference. We're going to select the level of significance. We're going to select 0.015. And then we're going to select the tested statistic. Again, we're going to be using chi-squared since we're all about proportions. And formulate the decision rule. We're going to reject x squared if it's 7.815. Again, because we only have 4 samples, our degrees of freedom is 3. So it's still the same as prior example. Next, we're going to interpret the results. Okay. So, using the same formula, this is why we would put it all in Excel and let Excel do its thing. We're going to have the observed minus the expected. Then we're going to square it. Then we're going to divide it by the expected and find the total. So 1.3723 is less than 7.815, so we do not reject. So the results are there is no evidence of a difference between the local and national experience for the hospital administration. Nice. So, what does chi-square have on limitations? If there is an unusual small frequency in the cell, chi-square might result in an erroneous conclusion. A very small number of denominators can make the quotation quite large. For only 2 cells, the FE should be at least 5. So we have to be at least 5 expected. So for more than 2 cells, chi-square should not be used if more than 20% of FE cells have an expected frequency that is less than 5. Okay. So, to give an example of this, we have the level of management. Notice that the issue can be resolved mostly by combining categories, but we have 3 out of 1, 2, 3, 4, 5, 6, 7, which is more than 20%, that are under 5. So what we'll probably do is combine them as vice president category or something along that line so that we can satisfy the 20% seat. So that's what they did here. They combined, but we do have to watch out for those ones that are below 5. It's actually, they just did the same chart, but basically all they did was combine. They kept an eye out for that. Contingency table. We can use a contingency table to test whether 2 traits or characteristics are related. The expected frequency will be determined as follows. So, FE equals row total times column total divided by grand total. The degrees of freedom, row minus 1, columns minus 1. So, example that they have here, of course, is just giving you the question, will be Ford Motor Company operates the Dearborn plant with 3 shifts per day, 5 days a week. Vehicles are classified as to quality level, acceptable or unacceptable, and shift, day, afternoon, night. Is there a difference in the quality level in the 3 shifts? Okay. So, our actual table that we're going to use. Rainbow Chemical Inc. employs hourly and salary employees. The Vice President of Human Resource surveyed 380 employees about their satisfaction levels with the current health care benefit program. The employees were then classified according to pay type, salary, or hourly. Is it reasonable to conclude that pay type and level of satisfaction with the health care benefits are related? Whew. Okay, here's our table. Pay type, satisfied, neutral, dissatisfied, totals. So, step 1, since we're testing, our null is that there is no relationship between level of satisfaction and pay type. Alternative is that there is a relationship level between satisfaction and pay type. Again, we're going to use a level significance of 0.05. And because we're using all this nominal data, chi-square is coming in for our test statistic. So formulate the decision rule. We're going to reject the null if chi-square is greater than 5.991. How do we find this out? We took degrees of freedom, R minus 1 and C minus 1. So, R, row, was only 2. Columns, there was 3. So, 2 minus 1, 3 minus 1 equals 2. Okay. So, again, using our chart, I think they had the chart all the way over here. 0.052, that's where they got the 5.991. It's just right there. Next, we're going to make the decision. Chi-square is going to be 2.506 by taking the row total, which is 55, and times the column total divided by the grand total. So 55 divided by 170 equals 24.61. Okay. So they took the sum. And they did this basically for all the expectations. And then they added them together. Comes out to 2.506. Yeah. Fun part right there. So here's the overly, here's the expected. So they had to do it for each one. Nice. So interpret the sample data does not provide evidence that the pay type and satisfaction level with healthcare benefits are related. So there's our chai. So we have made it to the practice problems, the last set. So starting off first, the U.S. Department of Transportation estimates that 10% of America is carpool. Does that imply that 10% of cars will have 2 or more occupants? A sample of 300 cars traveling southbound on New Jersey Turnpike yesterday revealed that 63 had 2 or more occupants. At the 0.01 significant level, can we conclude that 10% of cars traveling on New Jersey Turnpikes have 2 or more occupations? Okay. So, again, we're going to state the nulls. The null is pi equals 0.1. Alternative is pi does not equal 0.1. We use the significance of 0.1 as our level is chosen. Okay. So remember, this is a two-tail test. So that 0.1 actually gets divided by 2. So 0.01 by 2. So we're kind of using a little bit longer one right there. So let's go find our chart. Oh, give me a sec. Okay, now that the book is reloaded, let's go to our Z. Okay. So since we got calculator, 0.005 minus 0.5, we'll look at 0.495. So find our number. .495. Getting close. There we are. Again, cannot go over. Alright guys, so the book decided not to do divide by 2 on this. They're actually doing 0.01 as the significant level, and they're going to subtract that. So to do less confusion, we're going to go ahead and do that. So we're going to go ahead and take 0.10 minus 0.5 will give us to 0.4898 because it's below 0.49. So it's 2.32 as our Z stat. Okay. Well, we're going to be using that. So 2.32. So that's our critical value. So we're going to reject Z if it's greater than that. Figuring that there's a slight error going on here, but we're going to keep with the book. So next is to calculate the fun information of proportions. So Excel is coming for us. And we know right away that Z is going to always equal to our proportion. So successes minus observations. So we got to have both of those. So I have 63 and we had 300. So the formula that we're going to use to calculate our Z, so Z equals (63) divided by our observations minus 0.10, so our percentage. So we'll go ahead and make that a separate item. So our pi, we'll put the number in after we get the information in. Divided by the square root of pi multiplied by 1 minus the pi, close, divided by our observations. Okay, there we go. Hit enter. And we'll say it cannot be divided because we haven't put pi in, which is 0.10. So we come out to 6.35. Now, every time I do this problem, I'm only looking for the Z statistic for 1. I have all the information already in. Yay. So this is Z put for 1 sample. Okay, so we reject the null, so we conclude that the proportion of the carpool cars on the turnpike is not 10%. Okay, next question. Question 7 says the null of the alternative hypothesis are okay, we got pi 1 and pi 2, so we're going to compare the two. A sample of 100 observations from the first population indicates that x1 is 70. A sample of 150 observations from the second population reveals x2 to be 90. Use the 0.5 significant level to test the hypothesis. So, our decision rule. Again, all the way back here. Is going to be right here. So we know what them being equal. We'll have 1.96 as our z value. Again, a two sample test, and we have them equal. So z is going to be less than negative 1.96, and z is greater than 1.96. According to our little item. Now, so that was if it was a two-tail. Is this really a two-tail? No, it's not a two-tail. So, try and get a little bit lucky there. But, using our handy dandy table, we actually know it's one tail. So, calculator, 0.5 minus 0.05 will leave us with 0.45. So we need to go find that number. Remember, it can't go above. So it's right here in the massive sea of colors. So it's 1.64. So we had to watch out for that. Remember the difference between two-tail and one-tail. Okay, so we're going to reject the z if it's greater than 1.64. Okay. Next, we're going to have to compute the pull proportion, compute our test proportion, and define what we're going to do. Okay, so that means we're going to use this Excel. Okay, first we got to get to our formulas so we can input them. So here's our formulas. So back to our Excel. So this is for our one sample. Go rename one sample. Now, two sample. Two sample. Okay. Make it a little bit bigger. And of course, since we're just doing this, and we're not into chi-square yet, we're going to make it a little bit easier for us. So, sample 1. We're going to put successes. Sample 2. Sample 1. Observations. And do the same for sample 2 and sample 2 successes. And sample 2 observations. Nice. Next, we know we need those. Let's see, what do we need for the pool? We don't really need anything for the pool. Pool is a calculated one. Okay, so first off, we're going to do is proportion of 1. So we're really just going to put P1 and P2. Okay, you can label them any way that helps you out. I'm just doing it this way. So this is going to equal to this box, successes divided by observations. And this is going to equal to sample 2 divided by observations. Notice I'm building the formulas already in, so once I put in the numbers, it's going to calculate. So we're going to put this as the pooled proportions. And this is going to equal to, in parentheses, the number, not that one, sorry, number of successes plus number of successes divided by, in parentheses, number of observations plus the number of observations. Okay, there's my pooled. Now, the big bad boy, the Z test statistic. So this is going to equal to, in parentheses, are P1 minus P2 divided by, now here comes the fun part, the square root of our pool minus, actually we're going to make this simpler. We're going to make this simpler. Okay? So it's going to hate me for right now. That's fine. I'm just going to square root of 1. Well, yes. Alright, so we're going to make this a little bit simpler with the square root because it is a lot of information. So I'm going to put this as Z in 1 and Z in 2. So we don't have to put them all in one formula. We'll put them separate. So this is going to equal in parentheses the pool times 1 minus the pool divided by our observations. This is going to equal to basically the same thing. So I'm just going to copy this. Except we're going to put it as observation 2. Okay, so now when we do the square root, we can just tell it to add those two together. A lot easier, shorter on the formula, separates everything out in case there is an error that happens. So, now that we got our formula built in, let's put in our information. So, we indicate that a sample of 100, notice how it's going to fill in. We had 70. Next, successes, we had a sample size of 150. And successes of 90. So there we go. So our pooled is 0.64 and our z-test is 1.61, which is less than 1.64. They're very close. but we do not reject the null. Now we got formulas built in for one sample and two sample proportions. Okay. Question 19. A group of department store buyers viewed a new line of dresses and gave their opinion of them. The results were outstanding, excellent, very good, good, fair, undesirable. Okay, number of buyers. Because the largest number, 47, indicates the new line is outstanding, the head designer thinks that this is a mandate to go into mass production of the dresses. The head sweeper, who somehow became involved in this, I love how that, believes that there is not a clear mandate and claims that the opinions are evenly distributed among the 6 categories. He further states that the slight differences between the various counts are probably due to chance. Test the null hypothesis that there is no significant difference among the opinions of the buyers at the 0.01 level of significance. Oh, hey. So how do we do this? Well, first, we need our chai. Alright, so we know this all broken down, but we gotta find our degrees of freedom. Well, remember, degrees of freedom is taking the number of items that we have, and we have 6, so that minus 1 will give us the 5. So let's look at our chart. Okay. T, F, F. Here's our chi-square. So again, we say we're at 5. We are using 0.01, so all the way over here. So we'll look at 15.086. So we're going to reject the null if it's greater than 15.086. Fun. Right, now, let's build everything into Excel. So remember, this is our table that we're going to use. So, Excel. We're going to make this rename to chi-square equal make sure we go to the chart that had equal. Remember, everything is expected. So FO, this is our basic numbers, so we're not going to really mess with those. FE, so these two we will have to input no matter what we do. Now we have FO minus FE. So this will equal, oh, my bad. This will equal whatever this is minus this number. Okay? And we're going to drag that down because we're probably not going to have that many observations, but that will give us a key in case we need to adjust. Then we're going to take FO minus FE and squared. So the easiest way is to take this number and multiply it twice instead of using the power formula. And we're going to scroll that down. Alright, next, in this wide world of sports, we're going to take FO minus FE squared divided by FE. So this is going to equal, whatever this number is, divided by this number. We're going to scroll that down. Okay? And then our square value is a sum. A little bit too far. There we go. Formulas, auto sum. Okay, so let's go ahead and start filling in the numbers. So going back to our chart, right here, Excel. All right, so the number of observations that we have is 47, 45, 40, 39, 35, and 34. All right, so what we're running into is that we need to know the total. So again, I could go all the way down here. We'll go ahead and delete these rows. Okay. All right, so then we can adjust. We can always adjust according to the numbers, but this will make it a little bit easier. So for us, we know we need an even distribution. We have 1, 2, 3, 4, 5, 6. So this is going to equal to 240 divided by 6. So there you go. There's our chart for an equal. Now, because we have to input these two numbers, those are the two numbers we have to figure. Our chi-square ends up being 3.4, which is less than 15.086, so there is no difference in the proportions. So we can probably go ahead, and since there is no difference, it really is a game of chance with this. Okay. So again, now I've built the chi-square for chapter 13, or 15. I don't know. I'm stuck on 13. The regression. Okay. From experience, the bank credit card company, card departments of Carolina Bank knows that 5% of its cardholders have had some high school, 15% completed high school, 25% have had some college, and 55% have completed college. Of the 500 card holders whose cards have been called in for failure to pay their charges this month, 50 had some high schoolers, 100 had completed high school, and 190 had some college, 160 had completed college. Can we conclude that the distribution of the cardholders who do not pay charges is different from all others? Okay, so let's first count how many categories we got. We have 1, 2, 3, 4. So using our chi-square chart, we have 4 minus 1, so we're at 3 at 0.01. Or are we at 0.01? Yeah. So we are going to reject the null if it falls right here. Yeah, 1, 2, 3, 4. Yeah. So at 3, we're going to reject the null at 11.345. Let's make sure. Yeah. So it looks like if you are looking at the PowerPoint and looking at the answers they're giving, they are off on this one. Because they're using 0.01, not point. Yay. Anyway. So for our chai. Yeah. So using the 0.1 significance. Okay. So from there, we're going to go ahead and calculate. So getting our Excel back in order. Now, really the only difference between the equal and unequal. I'm going to actually copy this one and rename it as unequal. Is that we have to compute the expected value. So here we can actually do this as equal to basically our total here multiply proportions. So I'm going to put it right there as proportions. Our ratio, yeah, proportions. All right. So for me, we know we have 5, 50. Oh, we got to put them in percentages too. So 0.05, 0.15, 0.25, 0.55. So we're only left with 4, so we're going to have to adjust and remove these two. There we go. Next, we're going to insert the actual people. So this was 50, 100, 190, 160. So that's going to be the run-in. We're going to have to adjust these so that they all run on that total. Quick adjustment. And we come out to 115.224. So we are going to reject the null. Proportions are not as stated. Again, that was just like right here. We've done everything. We subtracted. Same thing. The only difference we had to do between two is basically do the proportions. Once we've calculated those in our Excel, boom. Now I have both unequal and unequal. Just the difference is proportion. Okay, last question of 15. Hi, the Quality Control Department at Foodtown Inc., a grocery chain in upstate New York, conducts a monthly check on the comparison of scanned prices to post prices. The following chart summarizes the result of a sample of 500 items last month. Company management would like to know whether there is any relationship between error rates on regular price items And specially priced items. Use the 0.01 significant level. So here, we have our little items right here. We got 2 columns and 3 items. We're doing the contingency table. Hey! So, back here, we'll have to make sure we have our rows and we have our columns. Again, degrees of freedom. Rows -1, columns -1. So, Excel. We're going to go copy again because it's going to use the same info. Create a copy. Okay. So this is chi-square. Name. We're going to call it contingency table. Okay. So we'll have to take rows -1, columns -1 for degrees of freedom. So, how many rows? How many columns? And degrees of freedom is going to equal to wherever this is, -1 times wherever this is, -1. Okay, so there's our degrees of freedom. Here, we don't need this anymore. Don't have proportions. Our FE, again, we'll have to put these in, will equal to rows total times, and we got column total and grand total. So FE equals now to this times this divided by this. Okay, I want to take this, take it, copy, paste, paste, paste. Okay. So r chi-squared is going to be the same thing. It's going to be a little bit different. But we're going to try and build it out just the same. Alright. So first off, let's figure out our degrees of freedom. So number of rows is 3. Number of columns is 2. So -2. So again, can't really be negative. It has to be positive. So we have to switch it to positive. So +2. So to our table we go. So 2 at 0.1. We're looking at 9.210. Okay, so that is our critical value. Next, we get to have the fun of taking down these numbers. So, using the formulas that we have. First off, expected. We have 20, 15, 200, 10, 30, 225. So we got a little bit more that we got in. We're going insert. Alright, so let's see if we can get these all figured out. So, we're going to have 3, so these were columns. We have 3 rows. Okay. Whoop. So, first thing that we have to do is row total, column total. So we're taking each one. Actually, we should put this in a chart. So, this one may actually take a little bit more time to actually piece together. Alright, so, row total is 30. Okay, 30. Column total is 20 plus 15, that's 35, 235. So grand total is 380. Yeah, okay, probably best to go ahead and put this in Excel. It looks like we're going to have to do each one. So, Excel, 20, 15, 200, 10, 30, 225. Okay. Auto sum. Auto sum. Alright, so we're looking at 500. Okay, so sorry. So that's for sample 1. So this is basically for undercharge. So they did 30 minus the FE expected divided by 2461. Then did 17 divided. So that's a different column. Ooh. So each column has their own item. Looks like. Oh, it looks like it's completely different for each one. Okay, so we'll have to do this a little bit more interesting. So we know this one is going to be 14.1. Because that is the expected. So next, is the next row. So yeah, we're going to have to do this individually for each one. So we just need to have this as a calculator. And we're going to have to manually input these. Unless you really want to make it completely complicated. So 30 times this divided by this. All right. So for 15, that is 45. 235 divided by 500. That's 21.15. Okay. Next is the 200. So that's 425 for its row. So that is going to be 199.75. Next, we're going to take the 30 again. 265 for its column. So that one is 15.9. Next is 45. So that's 23.85. And last row, we're looking at 265, or 225, sorry. Oh, that's 425. Sorry. So 225.25. Okay, so rows, column total, grand total. So that comes out to those numbers. Basically still doing the same info, same formulas. Get back to our Excel. And we're looking at 8.33. So this one, you pretty much have to have a subcategory. And you could, in theory, mask all this and make an extra chart that just does the rows and the columns, the totals. So these three, as you go through, that's no problem. But I mean, it's just easier. A little tie in and then have it already calculate what you got. So we do end up with 8.03. It is less than 9.21, so we do not reject, and that it is not a relationship between the error rates and the item type, or the regular price and the special price. Anyway, so that finishes up chapter 15. Let me know if you have any questions. I want to commend y'all all for completing all the lecture videos and all the chapters. It's been an interesting trip with y'all, learning a lot of information, learning that there's still a lot in Excel that we can still calculate with its software. But besides that, we're good to go. I wish y'all well, and I will see you either for another class. If not, I hope y'all have a wonderful rest of your college career and future careers that y'all would like. Okay, guys, y'all take care. It's been an honor serving with y'all, or honor being your teacher, and I will see y'all later.